So you've graphed your data. You don't have a straight line. What do? We can't use slope-intercept form unless it's a straight line, because how would you find the slope of something that looks like this, right? Honestly, the slope is increasing as we move along the x-axis, and so your slope is different at every single point. Yikes. What do we do? Your math teacher would say, oh, well, let's use calculus. Luckily, this is algebra based, and so we don't have to worry about that. We do have a trick. It's called linearization. It feels weird at first. It feels kind of confusing, but there's a list of steps that we will go through every single time we have to linearize a graph. It lets us put some extra work in by graphing it a second time with a different axis. But then we get to use our slope-intercept form again, which means it's something that we're way more comfortable with and way easier than calculus. So there's a summary side of all the steps at the end of this where it says physics toolbox. Write those down because we will come back to those over and over and over and over. And if this is confusing, which originally for most of us it is, if you have those steps handy, you will always know what to do next, even if it doesn't quite make sense yet. I promise it will at some point click and you'll say, oh my gosh, I figured this out. Why was I freaking out about it? It's going to take a different rate for all of you. It might take you hearing it from one of your peers before it makes sense, and that's okay. We've got time set up for that. We're going to do a lot of practice. So feel free to come to office hours with me, talk with your friends. We're going to get this figured out. So what do we do? Well, first we need our cheat sheet. This is in the folder called Linearization Cheat Sheet. You can use this at any point. I'm sure it's on Google if you search the same thing. These are the relationships that we're going to see in this class. There's a whole heck of a lot more. There's entire programs that linearize super complicated relationships for you. Because what we will find out eventually is doing this one time might not work. For us, we will only ever do it once, maybe twice, but some relationships require a whole heck of a lot of linearization. So these are the ones that we have to know how to do, right? We're pretty straightforward with this. This is what we've done. Same with this one too, right? We have a linear relationship. These might be a little bit new. So this tells us what is the relationship in words, an inverse, a square, proportional, those words that you use in math we'll see here. And then it tells you what do you actually do. This is why we call it a cheat sheet, which is pretty great. And then what you should end up with in terms of when you finally get around to getting to use slope-intercept form. So step one, graph your data. You've done your analysis, assuming you've done your experiment, you're graphing your data, you realize that probably does not look like a straight line. Sometimes it's not easy to tell, and what's going to help us is our criteria when we analyze based on our statistics here, right? We said the correlation needs to be as close to 1 as possible. Well, it's 0.8. That's bad, right? We should be very skeptical that this is not a good fit, right? All the points are under this data line, not good, I guess except for the end too. So correlation is bad. RMSE, remember our standard is we want this as low as possible. If it is below 5% of half of the Y max, which feels a little clunky, then it's a good fit. If it's above that, it's a bad fit. So half of Y max is 40, half of that is 20, 5% of 20 is 1. Is my RMSE less than 1? If it is, it's a good fit. If it's above 1, it's a terrible fit. In this case, we should be very skeptical of this fit, right? So we know we need to linearize. We're going to look at our cheat sheet, and our original graph looks like this. We're going to match it to the relationship we find here. I say it looks like this inverse relationship. As Y increases, X decreases. As X increases, Y decreases. I think I said that right. What do we have to do to linearize the graph? Well, we're going to graph Y, which in this case was volume. We're not going to change any of that. And then we're going to look at 1 over X, or 1 over pressure, right? We put pressure originally on the X-axis. It's an inverse relationship. So to get a straight line, we want to graph the inverse. So we are going to physically take our X data and put it in the calculator as 1 divided by 40, 1 divided by 20, 1 divided by 13 to get this data. Graphical analysis will do this for you. There's hints in that how-to guide, so feel free to just do it that way. But if we're doing it by hand, that's what we would do. And then once we have that, we're going to graph a second graph with this new relationship, 1 over pressure versus the volume. And if we look, 1 over pressure versus volume is a straight line. Hooray! Our analysis, I don't know if you can actually see behind the camera. It's clear for me, but I would assume it's not for you. If I click out of this, I'm going to lose it altogether. So our analysis, you can't see it, but our correlation is 0.99999. That's good. I'm not skeptical of that. The RMSE is 0.17. It should be lower than, remember our standard is 5% of half of the Y max. Y max is 40. Half of that is 20. 5% of that is 1. Is our RMSE of 0.1735 less than 1? Yes, so I'm not skeptical. This is a great line. I can use this now in slope-intercept form. And so step 4 now is to do what we've always been doing. Find the slope, plug it in to y equals mx plus b. We end up with y equals 200x, and my y-intercept is low enough that I can drop it. It's close enough to 0. Remember that standard is the same as RMSE. It has to be lower than 5% of the Y max. So Y equals 20x. Am I done? Never. We have to upgrade it now to a mathematical model. This is where we have to be really careful. We plug in, instead of saying Y, what did we put on the Y-axis? Volume. Instead of X, what did we put on the X-axis? 1 over pressure. Okay, so now how do we check to make sure that this equation is right? Well, we can pick a number from our original data, from our original curved graph, and see if it fits this relationship, right? Once we upgrade, being really careful to make sure we put that new manipulation in there, this equation is for our original inverse graph. So let's check it out. Let's see. Originally, the data point was 40 and the volume was 5. So if we look at our new mathematical model, let's plug in a pressure of 40. So it'd be 200 divided by 40, which, if I do my math right, is 5. Woohoo! So you can always go back and pick numbers from your original data set and plug those in to see if it fits your original graph, right? We don't really care about this straight line other than it's telling us the relationship is 1 over pressure. All right, so here are the steps you need to write down in your physics toolbox. We will come back to this over and over and over and over and over and over. If it's confusing, use these steps to help you until it makes sense. Okay, if you got questions, let me know. Good luck.